Okay, so we've got this nice little reaction here. Student calculates the enthalpy change for this reaction is 78 kilojoules per mole. In other words, that's delta H of the reaction. Now let's look at the reaction and think what we can say about delta S. Well, we've got calcium chloride .xH2O. That's a solid. So one solid goes to another solid plus X waters, where of course at 200 degrees Celsius, X waters are going to be gases. So we look at this and we would expect delta S of the reaction to be positive. So we've got positive delta H and a positive delta S. Positive delta H is nasty. Positive delta S is nice. So what does this tell us qualitatively about delta G? It tells us that delta G is going to be positive, nasty, at low temperatures, but then at higher temperatures, where the positive, nice delta S starts to win out, delta G will be negative at high temperatures. Okay, so low temperatures, not going to happen. High temperatures is going to happen. What's the difference between low and high? Well, it tells us right here that the minimum temperature is 200 degrees Celsius. So that implies that 200 degrees Celsius is where this reaction changes from non-spontaneous to spontaneous. And of course, as it changes from non-spontaneous to spontaneous, delta G is 0. So 0 delta G is delta H minus T delta S. Rearrange that, T is delta H over delta S, and of course we know the temperature is 200 degrees Celsius. Got to turn that into Kelvin, plus 273. We know delta H is 78 kilojoules per mole, so this will help us determine delta S. Delta S is positive 0.165 kilojoules per Kelvin per mole, as we expected, delta S positive, and of course nastier to give delta S kilojoules. Much more common to give it in terms of joules. So this whole thing depended upon the idea that at this minimum temperature, the feasibility or the spontaneity changes from non-spontaneous to spontaneous, or from unfeasible to feasible, and at that change delta G equals 0. Same idea with this one. Calcium carbonate decomposes on heating. Right, delta H plus 178 kilojoules per mole, delta S of the reaction plus 165 joules per mole per Kelvin. So first of all, we're going to calculate the free energy change delta G that is not feasible at 298. So we're given temperature, we're given delta H, we're given delta S. Pop in the values, do the usual change of joules to kilojoules for the delta S term. Delta G is plus 129 kilojoules per mole, which is of course a non-spontaneous, a not feasible process. However, as we saw in the last question, delta H is positive, that's nasty. Delta S is positive, that's nice. So as the temperature increases, the niceness increases, and at some point the niceness will overcome the nastiness. And at that particular temperature, delta G is 0, as delta G is changing from the nasty positive to the nice negative. So again, pop everything in. We know delta H, we know delta S, rearrange it to give us T, making sure that we get the units right, 178 kilojoules, 0.165 kilojoules. So T is 1079 Kelvin. So titanium 4 chloride, or TiCl4 as we call it, can be made from titanium oxide. There we are, we don't call that TiO or anything like that. Shown in the equation. So we have TiO2, 2C, 2Cl2 goes to 2CO gas plus TiCl4 as a liquid, delta H minus 60 kilojoules per mole. Some entropy data in the table, and when we look there we see we got the entropies of all the substances involved in the reaction. So use the equation there and the data in the table there to calculate delta G. Well, to get delta G, we need delta H and delta S. We're given delta H. To get delta S, we will do as we've done several times before. Just say, well, we know what the entropies of the substances, and delta S is the entropy at the end minus the entropy at the start. Pop in all the appropriate substances remaining to to bring in the stoichiometry. So we got 2 for the CO, 2 there, we got 2 carbons, we got 2 chlorines. Punch in all the values, into our calculator and we get 141 joules per Kelvin. Okay, let's do two things here. First of all, let us make sure that it kind of makes sense that delta S is positive, so there's an increase in entropy. Well, we got two gases and two gases, so that's kind of a wash. We got three solids, not very much entropy at all, and a liquid, more entropy. So therefore, in the balance, we're effectively turning three solids into a liquid. We look at the various entropy values of those. One of those solids, or actually two of the solids, very, very low entropy. The liquid has got a pretty high entropy. So overall, I would expect, yes, delta S to be a positive value. Now, the question also talks about significant figures. So let's make sure we're on the right track with those. We got 3, 3, 3, 3, and 3 significant figures. Okay. More importantly, though, is when you're adding up numbers, you give your answer to the least number of decimal places. So we got this here. This will be 3 sig figs with no decimal place, 1 decimal place, 2 decimal places, no decimal places. So our answer should be given to 0 decimal places. And here it is here in 3 significant figures as well. Now then we wanted to calculate delta G. So delta G, delta H minus T delta S. Temperature is 989 Celsius. Pop everything in. There's our delta H in kilojoules, delta S in joules. Here's our little addition to make sure we get the right temperature there. Change, of course, the joules to kilojoules. So it's not 141 joules, it's 0.141 kilojoules. Multiply all that out, and we get minus 238. And again, is the 3 significant figures correct? Yes, it is, because we got 3 sig figs there, 3 sig figs there, 4 sig figs, so we'll ignore that part. Okay. Again, what one should probably take note of is the fact that whatever this number turns out to be, you can only give your final answer to 0 decimal places, because this one had 0 decimal places when you multiply it out. Okay, and is this feasible? Well, yep, delta G is negative, so the reaction is feasible, spontaneous, etc. Equation for the reaction between ammonia and oxygen is shown. Nice one. Look at all those coefficients. We're told delta H, and here we are with all the entropies. So the first thing, calculate the entropy change. So same thing we've done many times before. Do not forget all of those coefficients. So 4 NOs, 6 H2Os, 4 NH3s, and 5 H2Os. Pop in the numbers, and we get 181 joules per Kelvin. Does it make sense? It's positive. We're going from 9 gases to 10 gases, so an increase in a gas. So I'm quite happy with a positive delta S. Part 2, calculate delta G at 600. So same thing again, we've done many times. Pop in delta H in kilojoules, get the right temperature, pop in delta G in joules, but then immediately convert that to kilojoules, punch it in, and delta G minus 1063. Now notice just the size of this. Delta H is a negative number, that's nice. Delta S is a positive number, that's nice. So delta G should be nice, and it's even nicer than the delta H's. Reaction between was carried at higher temperature. How does this change affect the value of delta G? Well, temperature affects the effect of entropy. Here the entropy is nice, so a higher temperature would just make it even nicer. So therefore delta G is going to also become nicer, which means more negative. So the last question, and I think my favorite because it has so many cool concepts illustrated in it. So we know delta G, delta H minus T delta S right there. A chemist investigates the reaction to determine how delta G varies with T, and here are the results. So we're plotting delta G on the vertical, it can be positive or negative. T, of course, in Kelvin can only be positive, that is along the horizontal. Now the first thing to notice is this is a straight line. Do we expect that? And the answer is yes, we do, because delta H and delta S are constants for a given reaction. It's not strictly true, but at A level it is. So what we've got here is we've got one of our variables equals a constant minus the other variable times a constant. So compare that to the equation for a straight line. If we plot delta G on the y-axis, as we have done, and we plot T along the x-axis, as we have done, well, then we're expecting a straight line in which m, the slope, is minus delta s, and c, right, the intercept, is just going to be delta h. So delta h here is the intercept p, so we got a negative delta h, okay? At this point here, delta G is 0, so at delta G is 0, that's the temperature at which the spontaneity changes. Now, do we expect the spontaneity to change? We're starting off with a negative delta G, going up to a positive delta G, and the reason it's a negative delta G at the start is because delta H is negative, but the reason why delta G becomes less negative, 0, and then positive, 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 getting worse and worse and worse, is because delta S, right, is a nasty negative. And the reason we know delta S is negative is because minus delta S, which is the slope, is positive. There are spontaneous when delta G is a negative and non-spontaneous when delta G is positive.